our series on the unification of physics. Now, last time we talked about non-relativistic quantum mechanics. It was really the first quantum theory, and it was designed to address the failures of classical physics. Classical physics, in several instances, did not accurately predict the physics at small scales. And so something had to be developed to remedy that, and the first theory that was developed was non-relativistic quantum mechanics. We've discussed these pieces of classical physics, and in the video today we're going to discuss Einstein's general theory of relativity, which will replace Newton's theory of gravity. And we'll also add a bullet here, and we'll discuss relativistic quantum mechanics, which is the next step along the way. Today we'll complete this side of the ledger, the classical side, with a discussion of general relativity. We'll also discuss relativistic quantum mechanics. That won't quite get us to the standard model, but it'll get us some of the way there. This is our goal. We want to get to this point. We can already see that there's a split between classical physics and quantum physics that still exists today. These two theories, general relativity and the standard model, are incompatible, logically incompatible, and we would like to find a way to unify them into one consistent theory, usually referred to as quantum gravity. That's what we call the unification of physics. And if you'd like to know more about this subject and go into more detail, you can go to my website at www.roadtoatoe.net. There you'll find 4 books that you can download and read, and it goes into far more detail than we can in these videos. So let's get to general relativity. Before we discuss general relativity directly, we're going to have to learn a few things about geometry. Now, you might not know this, or maybe you do, that there are really 2 kinds of geometries. One we call extrinsic, and the other we call intrinsic. So what's the difference? Well, extrinsic geometries have a fixed background. The one you're probably most familiar with is the Euclidean geometry. It has a coordinate system. This is the y-axis, and maybe this is the x-axis. And every point can be represented by x and y. That's its point in space, and that's its point measured from this particular point there. This is the point 0, 0 here. You don't really need to have Euclidean coordinates. You can have acute coordinates that look like that, or even ones that look like that. It doesn't really matter, although they're harder to work with. But the upshot, or the thing to take away from this, is that once we specify a coordinate system like that, all the points in this space remain fixed. And we usually say that the geometrical figures are embedded in the fixed background. So if we have a circle here, like something like this, it has a center. That center is a point, x1, y1, something like that. We can measure the distance from this point to any other point in the space. If we have any kind of a geometry, whether it's extrinsic or intrinsic, we need to have a way of measuring distance. How far are these points away from each other? For this particular fixed background, we measure distance using the Pythagorean theorem. And most of you are probably familiar with this. So if we have 2 points, there's x1, and we have another point, x2, y2. The distance s, we'll call it s, is equal to the square root of y2 minus y1 squared plus x2 minus x1 squared. Put this out over here. That's the Pythagorean theorem. If we want to extend this to 3 dimensions, if we have a z-axis coming up like this, we just put a z2 minus z1 squared. That'll make 3 dimensions, and if we want to make 4 dimensions or n dimensions. We just keep adding terms, and we still use the Pythagorean theorem to calculate the distance of one point relative to another point, or how far 2 points are away. And we can always do that because that background, that coordinate system or background, remains fixed. So if you hear physicists use the term metric, they're referring to some way in any kind of geometry to measure distance. We have to be able to do that, or we can't really talk about geometries, or we can't really do physics at all. Now, what about intrinsic geometry? Well, do we have a metric for it? Yes, we do. This is the metric for intrinsic geometries. Well, how does an intrinsic geometry differ from an extrinsic geometry? Well, for one thing, there's no fixed background. The metric in intrinsic geometries plays a dual role. Not only does it tell us how to measure distance in an intrinsic space, it tells us the geometry of the space. So it's this little piece here, tells us about what shape the space is in. We use the methods of the calculus. ds is equal to the square root of, integral here, ij dx I dx dxi dxj. Actually, we don't need this, we need this. This tells us the distance. It's the same thing as doing this. We have to integrate, and I'll show you why we do that in a minute. If we don't have a background, how do we define a point in a space? Well, let's take this little point right here on this line, and we'll call that S. That point is S. And we'll take another point here. And if we draw a straight line, if we had a fixed background, if we draw a straight line between those 2 points like that, we'd notice that, well, it's not quite, it doesn't quite marry up or match up with the shape of the space. How would we remedy that? Well, suppose we pick another point that's really close, right next to this point S. And if you look, the geometry of points that are really close together is almost a straight line. It's almost the Pythagorean theorem over here. Let's take this point really close to this other point, point S, and we'll call that point S plus ds. And the ds indicates to us that this point is extremely close to this point. Some mathematicians will say, well, it's infinitely close. But you'll notice that in order for us to define a geometry in intrinsic space, we actually need 2 points. We can't do it with 1 point. We can talk about 1 point over here. And in extrinsic geometry, we can't talk about a point in intrinsic geometry. The geometry has to be defined by at least 2 points. We want to ask what the distance is between this point and that point. And we can do that by just saying that S plus ds minus S is the distance between the 2 points. But this cancels with that. That's 0. And it just leaves us with this. It's the distance between 2 infinitely close points. And you can see that that looks just like that. And so part of what this metric does is it measures a distance along a curve. And part of what it does is it defines the shape of the space. And this is why we pick these 2 points. Then we use the methods of the calculus to add up all these little ds's here. And this tells this little piece here tells the geometry how to curve and how to shape itself. That determines the geometry of the space as well as how far we move along here. This line, for example, that just has the same contour as the shape of the geometry of the space is analogous to a straight line in flat space. If I were to draw a straight line over here, this line would be analogous to that because its curvature, the way it curves, is entirely due to the curvature of the space. It doesn't have any curvature of its own. If the line had curvature of its own, it wouldn't be comparable to a straight line. Now, they call these lines in intrinsic geometry geodesic lines. It's the same thing as saying that the curvature of the line is entirely due to the curvature of the space that's being defined by this thing here. And if that's the case, then the line is comparable to a straight line, or it's a geodesic line. And if it has curvature of its own, if it curves independently of the curvature of the space, then it's not a geodesic. That's how intrinsic geometries are defined. The metric defines not only a distance along a curve, but it also defines the geometry of the space. There is no fixed background. It turns out that more or less any kind of geometrical shape that you can make in extrinsic geometry, you can make in intrinsic geometry. What you can't do in intrinsic geometry is define position in space. This point here, if you were to ask me where this point is, I mean, it's not really valid in intrinsic geometry to describe something at a point. It takes 2 points to describe the geometry, so whatever happens at a point is undefined. That doesn't stop people from doing it. They talk about points in intrinsic geometries all the time, but technically speaking, you can only talk about what's around a point. You can't really talk about what's at the point. For example, in an extrinsic geometry, if we wanted to know the distance between a point and itself, s would be equal to 0, because y2 would just be y1, or vice versa. y1 minus y1 would be 0, and the same here, it would be 0, so the distance would be 0. So in intrinsic geometry, when we have a fixed background, we can say that the distance between a point and itself is 0. What happens if we try to say that in intrinsic geometry? If this is 0, for example, what that says is not only isn't there any distance between 2 points or between a point in itself, it tells you there's no geometry. The geometry disappears. We just lose the whole thing. In some exotic theories, that's exactly what happens, because this is roughly equivalent to 1 over something called the curvature of the space, which has to do with that. And if this curvature is infinite, goes to infinity, then this goes to 0, and you don't have a geometry. This is sort of the thing that happens when they talk about a black hole. When physicists talk about a black hole, they're talking about infinite curvature or close to it. And that's why they call it a black hole. It doesn't have a geometry. Why am I telling you all this? Well, it turns out that curvature of a geometry, which is what Einstein used to describe gravity, is an intrinsic property of a geometry. He used intrinsic geometry to describe his theory of gravity. And that's really important when it comes to discussing the unification of physics, because physicists have not found a way to describe elementary particles moving in space without first defining a fixed background. Nobody's been able to figure out how to do that. If you can't define particles without a fixed background, how do you unite physics on small scales with the physics on large scales? There's no fixed background here. And so all you have is just the fabric of space-time. And how do you create particles out of that? No one has been able to figure out how to do that. And so that's one of the challenges of trying to unite general relativity with some of the small-scale physics, is just for that reason. And that's true whether we consider string theory. String theory needs a fixed background, so far anyway. You need a fixed background to define a sensible string theory. This is a major hurdle to try to get over if we're going to unite general relativity with the small-scale physics. So let's start talking about general relativity. This is Einstein's equations of gravity. It's not important that we understand the nuances of this or what these things really mean to any extent. But the fundamental premise on which Einstein's theory of gravity is based is that the presence of matter and energy, which is expressed on this side of the equation, warps space and time, bends it. And so gravity is the warping of space and time in the presence of matter and energy. For example, you can see over here, here's the Earth, here's the moon. The grid is curved or deformed around these bodies. And again, we can't talk about a point specifically at the center of the Earth, the center of gravity, or anything like that. His equations only describe the warping of space-time around the body like this, around this body. How do we define matter and energy? Well, if you remember his famous equation, E equals mc squared. Well, this is the speed of light, so if we set c equal to 1, this would be just 1, and we just have energy is equal to m. So a mass like the Earth here is equivalent to energy. And so you would have a warping of the space around the Earth because it's a big mass. So this side of the equation would not be equal to 0, because there would be matter and energy warping the space and time. This side, if you look at this thing right here, remember that this is the same as that, and we remember, or we discussed, that this had something to do with the geometry of the space around a body or something like that. If you were to ask, well, is this the same as this? Yes, it is. You would guess from that this has something to do with the geometry of space and time. And if you guess that, you'd be correct. This side of the equation is the geometric side, the geometry of space and time. Geometry. And this side of the equation is the presence of matter and energy. So this tells space-time how to shape. This tells a ball or something how to move around the space. If we put a little ball around here, it would move in the contours of the warping of the space-time. How did this differ from Newton's theory of gravity? Well, suppose that Captain Kirk shoots a photon torpedo towards the Earth. Recall Newton's theory of gravity, we would have something like this. Over r squared, this would be the distance, r squared. Since light doesn't have a mass, this is the sun, by the way, and we're shooting a photon torpedo past the sun like that. One of these masses would be 0. That would mean the force would be 0. And so Newton's theory would predict that the photon torpedo would just shoot in a straight line like that and would not be affected by gravity. Einstein said, no, if the sun is there, it warps the space and time around it. The photon torpedo would go in a curved arc. And that's basically how they proved that Einstein's theory was better than Newton's theory. One of the ways they did it was when the sun isn't there, this space is relatively flat, there's not a bunch of curvature, so the photon torpedo would cover the same course as Newton predicted, but when you put the sun there, light from a distant star would look like it was coming from here instead of from here. And that's what they did. Without the sun present, they saw a star at that location. They waited for an eclipse of the sun where they could see this star when it was dark, and they found that it was over here. And so that's how they knew, or one of the ways they knew, that Einstein's theory was better than Newton's theory, because he correctly predicted that the sun would warp space and time. So that's pretty much what Einstein's theory says, how matter and energy warp space and time. This is the geometry on this side. This is it's called the energy momentum tensor. And the fact that Einstein's equations are tensor equations, talk about a little bit about that in a minute. Matter and energy. Suppose that we remove the Earth and remove the moon out of the picture, so we don't have anything in there. All right, so we could say then that this side of the equation, since there's no matter and energy, would be equal to 0. If we look at this little number right here, that's an r, that's called the curvature scalar. If this curvature scalar is 0, then the space is said to be flat. If r is not equal to 0, this r here, then the space is said to have curvature. If we set r equal to 0, then what we're left with is something like this. This RAB is equal to 0. This represents what physicists call a Ricci flat space. There are some geometrical figures that don't look flat that are flat, and I'll give you an example here. Suppose we have a cylinder. If we cut the cylinder with a pair of scissors, cut it up that way, and lay it open, it's basically a rectangle. And a rectangle is flat. Another example might be a donut. This donut, if we cut along here, we're just talking about the surface area of the donut now, not the meaty stuff inside. And open it up, it becomes a tube or a cylinder. And we can cut the cylinder down like that and open it up, and it becomes a rectangle. If you hear physicists say that geometries are topologically equivalent, that's what they're talking about, is that if I can make a transformation, if I can transform one of these shapes into a shape that looks like that, for example, those geometries are topologically equivalent. That's what they call it. While these geometries or geometrical shapes don't look flat, they are flat. We could ask whether a cone, something that looks like this, is flat. And the answer is, it's not flat. How do you make a cone? Well, you take a circle like this, and you cut out a little piece of this, and then you marry this point with this point, and that makes that shape. And notice what we've had to do here. We've had to remove some of the surface material. And if you have to do that, that's a surface area, for example, that is not flat. This would not be equal to 0. And so that's sort of an intuitive way of understanding Ricci flat from curved spaces, is that if you can take a geometrical figure and make it look like something like this, then you can say, well, those three geometrical shapes are topologically flat. But if you have to take surface area out of the figure to flatten it, then it's not flat. It's got curvature. That's how you tell the difference between what is known as a flat space and what's known as a space with curvature. Now, I mentioned that Einstein's equation was a tensor equation. Well, what does that mean? Well, what it means is that no matter what the geometry, Einstein's equations are invariant. In other words, they don't change because these are tensors. If you hear a physicist say Einstein's equations are invariant under allowable space-time transformations, that's what they're talking about. Since Einstein wrote his equations in tensor equations, those allow for changes in space-time geometries. In other words, this is certainly a different space-time geometry than this would be, because there's different masses and energies there. Einstein's equations would still describe each one of those situations equally well. And so that's the magical part and the really nice part of Einstein's theory. If you look at these pictures where there's a deformation of the space-time around the body, if you have a really flat, one of these really flat ones out here, but you get up close to a body, then these space-time little cubes are deformed, and it's, kind of this angle here, whatever it is a measure of the curvature of the space. Any deformation from a rectangle like this, then the angle between, if you extended this out, the deformation is a measure of the curvature around the body. And that's essentially what happens, is how they measure it. Again, we have to remember that curvature of space-time is an intrinsic property of a geometry. And so we don't need a fixed background to describe the curvature around bodies. It's a field theory. In other words, it describes the local conditions. It's not action at a distance where we have to describe something way over here. And so that's pretty much Einstein's theory of gravity in a nutshell. There's something else I should mention. If this is 0, in a universe now without any matter and energy in it, that's kind of a hypothetical situation, but we're going to imagine that we live in a universe that doesn't have any matter and energy in it. The right-hand side of this equation would be 0. And we want to ask the question, does that have to be equal to 0? And the answer is no. We could, in fact, live in a spherical universe. And we don't know whether we do or not. Whether the universe is spherical or is shaped or not, we don't have any idea. But if the universe was spherical in nature, this r would not be 0. It might be really small, but it wouldn't be 0. And so you can have a geometry that's not flat, even though there's no matter and energy in the vicinity. That's kind of interesting. It's also kind of a bugaboo. And the reason that it is because you might have heard physicists talk about string theory. String theory is the most promising candidate for a unification of physics. In other words, for unifying general relativity with the standard model or something close to the standard model or a reasonable facsimile of the standard model. The issue is the only sensible string theories that we know about today are ones that are defined on a Ricci flat space. R has to be equal to 0. And the question is, according to Einstein's theory, R doesn't have to be equal to 0 even if the right side of the equation is equal to 0. That's not a requirement. The question becomes, how does string theory emulate Einstein's theory of gravity in such a way that this gets included in there somehow, or maybe it doesn't. Maybe we can convince ourselves that if this side is 0, this has to be 0, but that's not required in Einstein's theory. And so that's another bit of information you can put away that makes it difficult to unify general relativity with the small scales physics, because Einstein's equation has this piece in here in addition to what we can describe in string theory. Einstein also added something called the cosmological term here. I'll put an AB here. It goes in here somewhere. There's a plus here. And I haven't talked about it because it's not important. At this point, it accounts for the expansion of the universe and things like that. We're not going to get into that because, again, it's not important for this discussion. But what you have to take away from this, to summarize, is that the right-hand side of the equation of Einstein's equations talk about how much matter and energy there is at a locale. The left side describes the geometry of space-time around that energy source. And so that's general relativity in a nutshell. So here's where we are in our journey. We've pretty much finished this side of the ledger. We added the general theory of relativity. The general theory of relativity has now replaced the Newtonian theory of gravity with a field theory. Gravity in this theory is the warping of space-time in the presence of matter and energy, and not the action at a distance that Newton thought it was. So we're done over here. Over here, we still have a little ways to go, and what we're going to discuss next is relativistic quantum mechanics. And we're going to add this bullet, and that'll get us a little further towards talking about the standard model of particle physics. Relativistic quantum mechanics was developed by Paul Dirac. He was a British physicist, brilliant guy. And what he did was he unified the special theory of relativity, that's Einstein's special theory of relativity, with non-relativistic quantum mechanics. So he made a relativistic quantum mechanical theory. What that meant was really, if you remember, Schrödinger's theory could be divided up into 3 wave functions. Now, these 3 wave functions came out of the theory, but if you remember, we had to put in by hand something called the spin wave function, or the spin number, in order to completely describe the way electrons behaved around the nucleus of an atom. But that's not the case with Dirac's theory. Spin arises out of the unification of special relativity with non-relativistic quantum mechanics. It becomes part of the theory. We don't have to put it in by hand like we did in Schrödinger's case. Dirac's approach predicts it. In fact, the wave function that Dirac used is called a spinner. He didn't call it wave function. He called it a spinner. And it describes all spin 1/2 particles, not electrons, of mass m. And this is Dirac's equation right here. This is what it looks like. This is Schrödinger's equation. Now, it looks different because we've written it down in spherical coordinates, but it's not all that different. If we put a bracket around here and factor out psi, get rid of that, and bring it out into the outside the brackets here. This part here, this part in these curly brackets here, that's just h bar. And then you have psi is equal to E psi, this. You should be familiar with that from the last video. It's an eigenvalue equation. Now the difference, one of the big differences between Dirac's approach and Schrödinger's approach is that the wave function in Schrödinger's approach was three-dimensional. You know, there were 3 parameters here. In Dirac's, as you might expect, there are 4 entries, four-dimensional function or a 4-dimensional wave function. And that should make sense because Einstein's theory was 4-dimensional, x, y, z, and t. So that was the big leap forward. Dirac's equation explained the anomalous Zeeman effect and the fine structure of the atom. And it also predicted another kind of particle called a positron, predicted antiparticles. Dirac's equation was, roughly speaking, a eigenvalue equation. This part here operated on that, so maybe we could put a hat over that. I don't see people doing that. And then it operates on the spinner, and then it gives an eigenvalue over here, somewhat like Schrödinger's equation. It's kind of got the same form. By the way, this equation and this equation are the same. I'll show you why. It's customary to set h bar equal to c equal to 1. So if this is equal to 1, and this is equal to 1, and you look over here and move this over to this side of the equation, this equation is exactly the same as that equation. So they're the same. So that was a leap forward with this unification of special relativity with quantum mechanics. Probably one of the biggest leap forwards that we've had in physics. There was one issue that Dirac's theory had, and that had to do with the Dirac sea. In his theory, there was nothing to stop positive energy electrons from emitting photons or light and becoming negative energy electrons. The question was, why did positive electrons exist at all? And of course, we knew they did. And so what Dirac hypothesized was that all of space was filled with this vacuum energy that is represented by this blue piece down here. And he knew that electrons followed the Pauli exclusion principle. So he hypothesized that this vacuum space was completely filled with negative energy electrons. And since electrons followed the Pauli exclusion principle, no 2 electrons could be in the same quantum state at the same time. That created a situation where positive energy electrons could exist. And they wouldn't all become negative energy electrons over time by losing energy. And so every once in a while, one of these negative energy electrons would pop out of the vacuum and become a positive energy electron, and it would leave a hole of a positive charge. Dirac first hypothesized that this positive charge was the proton, but somebody pointed out to him that the positive charge here, the mass of that hole, should be the same, couldn't be no bigger than a mass of an electron, and the mass of a proton was 1,800 times bigger than an electron, so the hypothesis that this represented the proton was given up. It wasn't accepted. A few years later, Carl Anderson, an American physicist, discovered the positron. Experimentally, the positron became a fundamental part of Dirac's theory. This idea of a vacuum state wasn't very popular with most physicists because it was unobservable. It was a metaphysical idea. It couldn't be tested. eventually in quantum field theory, which replaced relativistic quantum mechanics, so your quantum field theory. The positron, rather than a hole or an absence of a particle, became a particle itself. That didn't really remove all the problems of this vacuum energy. In quantum field theory, the vacuum state has an infinite amount of energy, and it requires renormalization to get rid of it. And so there's still problems with it, even though quantum field theory treatment of the positron is a little bit more acceptable than what Dirac proposed. So that's, in a nutshell, relativistic quantum mechanics. We've really completed our discussions of classical physics. We discussed Newtonian mechanics, Maxwell's theory of electromagnetism, basically the two great theories of the Enlightenment period. But there was a conflict between Newtonian mechanics and Maxwell's electromagnetism. It was removed by Einstein through his special theory of relativity, but it only applied to inertial reference frames. General relativity provided a theory of gravity that was a little better than Newton's theory, so the general theory of relativity became our theory of gravity and replaced Newton's theory of gravity. It also was a field theory. By doing this, there was a chance, it didn't happen, but there was a chance that electromagnetism could be unified with gravity. Classical physics failed to describe the physics at small scales. And so we talked a little bit about the development of non-relativistic quantum mechanics, which attempted to address the failures of classical physics at small scales. It had some shortcomings, and some of those shortcomings were addressed by Dirac with his relativistic quantum mechanics. It was a unification of special relativity with non-relativistic quantum mechanics. Again, it only applied to inertial reference frames, so it was consistent with the special theory of relativity. But it had this vacuum energy problem that somewhat still exists today. It's addressed a little more adequately in quantum field theory than in relativistic quantum mechanics, and we'll discuss those later on. So we still have a little ways to go in our discussion of the quantum side of the ledger. Now we are finished on this side of the ledger. We talked about how we got from Newtonian mechanics to the general theory of relativity. It's become our theory of gravity. In fact, it's become our theory on large-scale physics. We went some of the way towards the Standard Model. We've talked about non-relativistic quantum mechanics and relativistic quantum mechanics through Dirac's theory. And Dirac's theory pretty much addressed the way electrons move around the nucleus of an atom. So we had an adequate theory of the electrons, or how the electrons were configured around the nucleus of an atom. But what we did not have was a theory that addressed what went on in the nucleus of an atom. In the next video, we're going to talk about the theories that addressed what goes on in the nucleus of an atom. Please tune in.